Welcome back. Previously, we've looked at how signed and unsigned integers are stored in the computer. We've also looked at ASCII representations of character data. In this video, we look at how floating point numbers are stored. Floating point numbers are represented internally in a way that's similar to writing numbers in scientific notation, except in binary. Recall that when we write a number in scientific notation in base 10, we have a sign, positive or negative, followed by a single digit that's not 0, followed by a decimal part of the number, then multiplied by a power of 10. It's normalized if there's a single non-zero digit in front of the decimal point. In binary, we have a sign followed by the single digit 1, then a string of zeros and ones representing the fractional part, all multiplied by a power of 2. This describes how both float, single precision, and double precision numbers are stored. There is a standard, IEEE 754, that's universally adopted. This standard defines how to store single and double precision, and we see the ranges of numbers that can be stored in this representation. The format first has 1 bit for the sign, 0 for positive, 1 for negative, then a biased exponent, 8 bits for single precision, 11 for double precision, then the fractional part, 23 bits for single precision, more than double that, 52 bits for double precision. The 1 in front of the binary point is not stored since the number will always be 1. It can't be 0 because that wouldn't be normalized. The bias added to the exponent is 127 for single precision and 1203 for double precision. Notice that the placement of the fields helps in sorting comparisons. Let's look at an example. Imagine we can peek into memory and see this binary 32-bit number. What number is this in decimal? The sign bit's 1, so it's a negative number. The exponent, 1000001, is 129 in decimal. Once we subtract the bias of 127, this gives an exponent of 2. The fractional part is 0.01. When we combine this with the assumed 1, we get 1.01 times 2 to the power of 2. When we multiply by 2 to the power of 2, we get negative 101.0 in binary. This is negative 5 in decimal. Now let's go the other way. We'll start with a decimal number and store it in single precision format. We have to figure out the decimals. Just as we go left from the point, 2 to the 0, 2 to the 1, 2 to the 2, etc., when we go to the right of the point, it's 2 to the negative 1, 2 to the negative 2, and so forth. So the place values are like this. We can get 0.75 as 0.5 plus 0.25, so 0.75 in decimal is 0.11 in binary. We need to normalize this to get a 1 before the point. So now we have negative 1.1 times 2 to the negative 1. The exponent is negative 1 plus 127 equals 126, which is 011111110. Remember that we need to fill the 8-bit field for single precision. The 1 before the point is not stored anywhere. The number after the point is placed in the fractional part. And we put all that together in binary and convert to hex. Let's look at another example. Convert positive 14.75 to the single precision format, and I've outlined it here in steps. First, determine the sign bit. It will be 0 for a positive number. Then convert the whole number part to binary. 14 is 1110. Convert the fractional part to binary. That's 0.11. Put 2 and 3 together. 1110.11. Normalize. Calculate the exponent as the exponent plus the bias of 127. Convert the biased exponent to binary, then get the fractional part from step 5. Just as you can repeatedly divide a decimal number by 2 to convert it to binary, you can multiply the decimal part by 2 repeatedly to convert it to binary. I've created a spreadsheet here where we start with the fractional part and multiply it by 2. The whole number portion will be 0 or 1, which goes in the third column. The fractional part carries forward to the next row. This process is repeated until we get 0 in the first column or until the maximum number of digits is reached. 0.085 put into this same spreadsheet, and we stopped at the max number of digits and still didn't have 0 in the fractional part. This number can't be perfectly represented in single precision format. Next, let's look at a really nice site for IEEE 754 format. Here's a really nice site that can help you practice converting to floating point numbers. You can see the site up here, but if you Google IEEE 754 and then Schmidt, it should pop up with this link. So you can enter a decimal number in the box. So I entered 0.85 and hit enter. And we see the hex representation, the binary representation. It also tells us the actual number that was stored. So we couldn't store 0.085 perfectly, but we could store this number here. And it also has this display up here with little check boxes, where if it's unchecked, it's 0. If it's checked, it's 1. So you could simply change the sign by clicking on this box right here. And you can play with any of these boxes however you want. So notice that as our exponent gets smaller, we're getting about to the range of the numbers that we can represent. If we uncheck all of them, we get what's called a denormalized number. These are numbers in the underflow space near 0. We've seen that we can't represent every number perfectly, but there are other problems. Overflow can happen, meaning that the positive exponent we want to store is too large for the exponent field. Underflow means a negative exponent is too large. Double precision helps since it has a wider range of numbers it can represent. However, the primary benefit of double precision is greater accuracy. This chart from the book gives greater details about the 754 encoding scheme. Let's focus on the single precision. Exponents in the range 1 to 254 with anything in the fractional part or normal numbers. An exponent of 0 and a fractional part of 0 is really 0. This encoding is necessary because of the assumed 1 in front of the point. An exponent of 0 and fraction anything but 0 is a denormalized number. An exponent of 255 and a fractional part of 0 represents infinity. An exponent of 255 and a fraction of not 0 represents not of number. You may have done some math expression in a higher level language and gotten either not a number or infinity. This is where that came from. It's just special encoding to represent that. But what is a denormalized number? These are numbers near the underflow space around 0. For these numbers, the leading 1 is replaced with the leading 0, and the exponent is adjusted to represent them as closely as possible. Not every number can be represented exactly, even numbers that make perfect sense to us, such as 1/10. We see that even in double precision, it's not exactly 0.1. If we think about it, in a 32-bit field, we have 2 to the 32, or about 4 billion unique bit patterns. But there's an infinite number of reals between even 0 and 1. The IEEE standard doesn't guarantee that every number will be perfectly represented, but that every machine using the standard, which is all machines, will get the same results. The IEEE 754 standard specifies 2 bits that are kept to the right during arithmetic operations. These bits are in the circuitry, but not in the final result. The guard bit is the first extra bit to the right. The round bit is the second bit to the right. Further, a sticky bit is set whenever there are non-zero bits to the right of the round bit. These extra bits are helpful because if you truncated numbers before adding, for example, you've already lost some precision. When the fractional part, the mantissa, needs to be shifted to align exponents for arithmetic, some bits may shift off. These go into these extra bits. The IEEE format also allows for different rounding schemes, rounding up, down, truncating, or to the nearest even. During the first Gulf War in 1991, a U.S. Patriot missile failed to intercept an incoming Iraqi Scud missile, resulting in loss of life. An analysis revealed that a software counter had been updated every 0.1 seconds, and then multiplied by 0.1 to compute the actual time. Over 100 hours, the time was off by about 0.34 seconds, which doesn't sound like much, but that's enough time for a Scud to travel 500 meters. This is one of many examples why programmers need to understand number representation. Problems can also occur if one argument is much smaller than the other, since we need to match the exponents to add. In this case, we have numbers at the boundaries of what can be represented. 1.5 times 10 to the 38. What will actually happen is that the 1 gets rounded out of existence. Here's another example. X and Y are 1.5 times 10 to the 38 and negative 1.5 times 10 to the 38. When we add them in this order, we get 1. Well, the rule of arithmetic associativity says that this should also give us 1, but it doesn't, as we see in our output here, because this 1 was rounded out of existence when added to the Y value. To use floating point operations in MIPS, we use a different set of registers and different instructions. Before we take a quick look, here's a little historical background. In the early 1980s, Intel introduced the 8087 coprocessor. This was a separate processor to the main x86 processor. A lot of the IEEE standard is based on the 8087, and it was very influential on floating point processors. Today, in a modern CPU, the floating point processor is inside the main chip. However, it is a separate logical unit, and we can think of it as being a separate processor logically. In Mars, we have coprocessor 1, where all of our floating point registers are. So what we see is that there's 32 of them. They're numbered from F0 through F31. And we can access them as either single precision or double precision. We can access any register as single precision, but if we want a double precision register, it needs to be an even register, like F0, F2, and so forth. Here's a quick example, and then we'll get more in depth into the new instructions. Just as we used the .word assembler directive before to hold an integer, we can use either .float or .double to hold a floating point number. So this program is going to compute the area of a circle. I have pi and a radius. We're going to have different load instructions. So this is going to load the pi value into register F0 and the radius into F4. Notice that I used even registers because these are doubles. Then I multiplied the radius by itself to get my r squared, and then multiplied that by pi, and finally printed out. So let's run that program real quick, and we see it printed out my area here. I've created a spreadsheet to organize the new instructions. This will be handy reference when you do a floating point assignment. I'll share this under Resources. This spreadsheet has different tabs for arithmetic instructions, loads and stores, moves, conversions between number formats, comparisons, and branches. Let's look at the arithmetic instructions first. You see we have add, sub, mul, and div, and they're all followed by .s if we're using single precision registers, or .D if we're using double precision. So for each of these I have an example. Let's look at this sub, for example. I want to sub 2 floating point registers, so this will take F2 minus F3 and put the result in F1. We can use any floating point register. However, if we want to do the subtract on a double, we need to use even registers, and that's true for all these operations. There's also an absolute value and a negation. We need different instructions for load and store. So we have LWC1, that means load word coprocessor 1. Notice that this is C1, not CL. And here's an example. So here we're using a T register like we've done before to hold an address. And we're loading the contents of that address, which will be a word, which is single precision. We're loading the contents of that address into F1. If we wanted to load a double, it would be LDC1, loaded double into coprocessor 1. We'd have to use an even register. So again, we can specify the addresses the same as we have before with either a label or a register in parentheses. An address is an address. It doesn't matter if it's pointing to a word, a character, or a floating point number. So we can still use these T registers. We have 4 load and store instructions depending on if we're loading a single precision or double precision. And we also have these convenience pseudo instructions, a little bit less typing. L.S and L.D for load, and S.S and S.D for store. We have a couple of move instructions. Let's look at these down here below. These are moving between floating point registers. So moving between single precision would be move.S. Moving between double precision would be move.D. There are some times when we're going to need to move things from our regular processor to coprocessor 1 or vice versa. So we have 2 special instructions for that. MFC1, move from coprocessor 1, and MTC1, move to coprocessor 1. And the first argument R, this means one of our general purpose registers, and the second argument needs to be floating point. So for example, if we move from coprocessor 1 T1 F1, that will move what's in this 32-bit register F1 into T1. The MTC1 will do the opposite. It will copy what's in this general purpose register to register F1. We'll see some use cases for that when we get back to Mars. Sometimes we're going to want to convert between bases. Again, let's look down here at the bottom first. These are just simply converting between single and double precision. So all the convert instructions start with CVT dot, and then you have one letter indicating what you're converting to, another dot, and then another letter indicating what you're converting from. So this would convert from single precision to double precision, and this one would convert from double precision to single precision. Obviously, you would lose some precision there. And there may be times when we need to convert between integers and floating point. So to convert from an integer to floating point, we use this instruction. Let's look at the example. F3 would be holding an integer, and then we convert that to a floating point, single precision, and store that in F1. You can use the same register for source and destination. We're going to need new compare and branch instructions. So we have a few compares, and then the relation. We have equal, less than or equal to, or less than. That's really all we need because we could always swap the order of our registers. And then we have either .S or .D for either single precision or double precision. So the notes over here say what this does. For example, let's look at the CLE. Let's look at this instruction right here. All right, so this is going to compare F1 and F3. And if F1 is less than or equal to F3, then we're going to set C, a special flag register, to 1. All right, so after we do that, we can use one of these branches, BC1T, BC1F for false. So this BC1T will branch if that C that we set here with the compare is 1, and BC1F will branch if it's 0. Let's look at another example in Mars. This program will convert a Fahrenheit temperature to Celsius. Here's the formula we're going to use, and notice there's a lot of constants. So we have to decide how to set those up. In this program, I went ahead and named them constant 5, constant 9, constant 32, and so forth, and initialized them with a value. There's another way we could do that, which I'll talk about in a minute. If we go ahead and take a look at these in memory, you could see that these are stored as the 754 formats. You could actually copy one of these numbers and paste it into that Schmidt site to see what it is. The first thing we do in the program is load our Fahrenheit temperature that we want to convert, and then we load our constants. I have commented out loading the constant 5 to show you another way that you could do it. If we didn't decide to have our constants in memory, we could load integer 5 into a register, move it to coprocessor 1, and then convert it from integer to single precision. That would require 3 instructions, so that's part of the reason I decided to just load the 5.0 into memory directly. There is no load immediate instruction for loading directly into a floating point register, and you cannot load a floating point value into a general purpose register. These are your choices. Either use these 3 instructions or set up your constant here. After the constants, we're ready to divide the 5 by 9. Subtract 32, and then multiply and display the results. So let's run it real quick, and we see that our Fahrenheit temperature of 72 is equivalent to Celsius 22, etc. In class, we'll get a lot more coding practice, but I want to leave you in this video with a practice problem you can do on your own. Take these 2 numbers, calculate the average, and output them. Until next time, happy coding!